Welcome back. In the last lecture, we introduced you to what are called as alternating currents or alternating voltages, and we defined different terms associated with these. So, alternating current, and voltages. We considered first a simple circuit consisting of a resistance and a source of EMF, which is time varying. So this time variation was sinusoidal, V equal to V max sin omega t, and this is the resistance R, and the current I then is given by the standard expression for Ohm's law, which is V by R. So in this case is given by Vm by R sin omega t, which we write as I maximum times sin omega t. So you notice that the time variation of both the voltage and the current are the same. Both of them vary with time as sin omega t, and this means the current is in phase with the voltage. We had introduced a phasor diagram corresponding to a purely resistive circuit, and what we showed there was the following. We said that my x-axis is the time t equal to 0 reference line, and my both current phasor and the voltage phasor, they rotate counterclockwise with an angular velocity omega. So at time t equal to t, let's suppose this is my direction in which the voltage phasor is located. So this is a phasor of magnitude, let's call it OA. So OA magnitude was Vm, and therefore if you take the projection along the y-axis of this quantity, this gives you the instantaneous value of the voltage. Now since the current is in phase with the voltage, and I know that the current and voltages are measured in different units, supposing the in whatever units we measure I, that's of course ampere, but in whatever scale we measure I, supposing this is O times B is the magnitude of the current amplitude, then if you take the projection along the y-axis, this gives you I of t. You notice here that the voltage and the current are in phase, and so therefore the direction of the phasors are identical. So since the time variation of both the voltages and the current was sin omega t, we proved that the average of the current, also that of the voltage, over a cycle is equal to 0, and that's because sin omega t, sin 2 omega t, etc., their average turns out to be equal to 0. For a purely resistive circuit, what we found is P average is given by Im square R divided by 2, which led us to define something known as RMS current, root mean square current, which is defined as the maximum current divided by square root of 2. If you do that, the expression for the P average works out to be identical to the expression that we had in case of DC circuits. The concept of RMS is also applicable to, for example, the voltage, and you can talk about V RMS is V maximum by square root of 2. And I also told you that whenever we mention that the household voltage is, let us say, 240 volts, we don't always say it, but what is implied is that these are the root mean square values. So the peak voltage will be obtained by multiplying that with a factor of square root of 2. Having done that, we considered a circuit consisting of an inductor, and so this was my circuit. Once again, I have an alternating source, so my Vm sin omega t is the V of t, and this is L. And what we found in this case is that the current expression for the current is given by Vm divided by omega L times sine of omega t minus pi by 2. So this of course told us firstly that this is the magnitude of the maximum current, and the time variation is not in phase with the time variation of voltage, but the current lags behind the voltage by pi by 2. Returning back to a phasor diagram for this situation, so what we do is this: supposing this is my voltage, and so that the projection on the y-axis is my V of t, so this is V max, the magnitude. Then my current would be represented in this direction, so that this angle is 90 degrees. This is what is showing you that it is lagging behind the voltage by 90 degrees. So this is the length of this vector is I max, and this is your instantaneous I of t. If you notice that the expression for the current was given by I equal to I max times sine omega t minus pi by 2, and in this case Im is given by Vm divided by omega L. So in other words, the role of resistance in the purely resistive circuit is assumed by this combination here, omega times L, and this omega times L is called inductive reactance, and it is denoted by XL. So let's look at some example. Let me consider a resistive circuit in which the RMS value of current is 5 ampere. We are asking what is the value of the current. One over 400 seconds after it became 0. So since I am given the RMS value is 5 ampere, I can get the maximum value of current, which I call as Im, by simply multiplying with square root of 2. So 5 square root of 2 ampere is the maximum value of the current. Therefore, my I at time t is given by Im sine omega t and that's equal to 5 root 2. I also need what is the frequency of the circuit. So let me say that frequency of circuit f is equal to 50 hertz. So this is sine omega is 2 pi into f, which is 100 pi times t. So notice that at t equal to 0, the current is 0. And at t equal to 1 over 400 seconds, I get I equal to 5 root 2 into sine 100 pi multiplied by 1 over 400. That gives me sine of pi by 4, which is 1 over square root of 2. So this is simply equal to 5 amperes. Let me continue with an example, this time with an inductive circuit. I have a voltage source V equal to 25 sine omega t, meaning thereby that the maximum voltage is 25 volts in a circuit which corresponds to omega equal to 400 radians per second. This is approximately the type of radian frequency that you would get for a supply which is slightly more than 60 hertz, because corresponding to 60 hertz, omega turns out to be about 377 radians per second. But this we are taking simply just because it helps easy calculation. So this in a 10 Henry, with a rather large value I have taken, but again for simplicity, 10 Henry inductor. So let's find various things connected with it. That at the instant when the voltage is minus 12.5 volts and its magnitude is increasing, what is the value of current? This example will sort of help you understand various terminologies that I have been using. So first is the maximum value of the voltage Vm is 25 volts. From the given data, I can also find out what is inductive reactance. So XL, which is equal to omega times L, omega is 400 and L is given to be 10, so which is 4000. The unit of reactance happens to be just ohms. So maximum current then would be Vm divided by omega L, which is equal to 25 by 4000, and if you calculate it, it is just 6.25 milliamps. Obviously, the current becomes maximum when the voltage is equal to 0. That's because we said that the current lags behind the voltage by 90 degrees. Now let's look at what is the instant when voltage value is minus 12.5 volt and it is increasing in magnitude. Now look at what it means. So what it says is my V of t is minus 12.5 And the general expression for V of t is Vm, which is 25 times sine omega. So that tells me that sine omega t is minus a half, minus 12.5 divided by 25, it's equal to minus half. Now my angle omega t varies from 0 to 2 pi. So I know that the sine function becomes negative in third and the fourth quadrant. So my solution for omega t then happens to be either 7 pi by 6 or 11 pi by 6. That only takes care of the variation of V of t, but let's look at the other condition that is there, that the magnitude is increasing. Let's consider the way the voltage varies with time, and what I'm going to do is to plot the voltage not as a function of time but in terms of omega t, which as you know is measured in radians or degrees, whatever. So this is omega t equal to 0, and let me plot the voltage like this. This is just one cycle I'm showing. Now, so this is 0, this is of course the phase. Remember, I am doing it in terms of omega t. This is pi, this is 2 pi, corresponding to time t by 2 and the full cycle t. So this maximum here we have said is 25 volts. Now we are looking for the voltage becoming minus 12.5. So roughly I am looking at half this value. So this will be either a point here or a point there. Now what we want is V of t equal to minus 12.5 volts and its magnitude should be increasing. But if you look at it, minus 12.5, so this is minus 12.5, is here as well as there. Now if you just look up a table and find out where does it actually occur, you will find that this is occurring at omega t equal to 7 pi by 6 and 11 pi by 6. And that's purely because this magnitude is half of the maximum value, and this is just because what we are looking for is minus 12.5, which is just half of the maximum magnitude, and so therefore it is I'm looking essentially for values of angles for which the sine of the angle is minus half, and so these are the two angles. Now out of this I pick up 7 pi by 6 because that is the place where the voltage is increasing in magnitude. This is also satisfies the same value of minus 12.5, but there you notice that the magnitude is actually decreasing. So therefore this value 7 pi by 6 is what I have. So the magnitude is increasing at omega t equal to 7 pi by 6. So my current I is then given by maximum amplitude of the current 6.25 times sine of 7 pi by 6 minus pi by 2, that is because of the lag, which is equal to 6.25 sine of 4 pi by 6. Sine of 4 pi by 6 is square root of 3 by 2, and if you calculate this, it will give you 5.41 milliamps. Having explained how a purely inductive circuit works, let's consider a purely capacitive circuit. with the same alternating source as before. So this is Vt equal to Vm sin omega. Now this case would be different from the way the capacitors behave under a DC supply, because in a DC what happens is a capacitor behaves like an open circuit and doesn't allow the current to pass through. So all that happens is there are transients created and the capacitor plates get charged, and once they are fully charged they remain so as long as the battery remains connected to the capacitors. Now here what happens is this, that assuming that initially my capacitor plates are uncharged, there would be a charging current. And this charging current would make this capacitor plate, let's say this plate positive, this plate negative. And as the voltage keeps on changing the direction, and so does the current, so I will have alternately charging and discharging. So this thing is given by dq by dt is equal to C dV by dt. So this is my charging current, and this is what is going to flow into the capacitor. And so therefore what I have is that my voltage difference between the two plates, since there are no other elements in this circuit, this is the same as V of t. So what I get is my V of t is given by the instantaneous Q of t divided by C. So therefore Q of t is C times V of t, which is equal to C times Vm times sine of omega. And then my charging current I of t would then be, I need to differentiate this because dq by dt, so it is C Vm omega cos omega t. And I will rewrite this as Vm times C omega. Now cosine of omega t I would write as sine of omega t plus pi by 2. So if I write this current as equal to Im sine omega t plus pi by 2, my current amplitude is given by Vm times C omega. Therefore, the ratio Vm by Im is 1 over C omega. So notice that the role of resistance in a DC circuit is played by this factor 1 over C omega, and that is usually denoted as Xc, and this Xc is known as capacitive reactance. So let me make a note here that Xc is equal to 1 over omega C is equal to capacitive reactance. Notice one thing, just like the case of the inductive reactance, capacitive reactance also depends upon the source frequency. So the variation, now if I am plotting capacitive reactance Xc, which is equal to 1 over omega C, so that would be going like this. So that is your Xc. Now Recall that my current amplitude I of m is Vm divided by x, which is Vm times omega c. So if in the same plot, if I am plotting the behavior of Im, this is just linear. The amplitude increases with increasing frequency. Let us look at the variation of voltage and the current for one period. So this is the way the voltage varies, and let me just show quarter of cycles separately. So this is t equal to 0, this is t by 4, this is t by 2, this is 3t by 4, and this is t. So let me show the current in the same diagram. So this the black curve is V of t, and the red curve is the current I of t. So you can see that the current has become maximum a quarter of a cycle before the voltage does. So our variations would be as follows. If I take V of t to be equal to Vm sin omega t, then the corresponding current is given by Im sin of omega t plus pi by 2. So since the current leads the voltage by pi by 2, it would have become maximum a quarter of a cycle, that is capital T by 4, before the voltage reach. I just want to point out that these are representative curves, in the sense it is not as if the voltage is switched on at time t equal to 0, but basically as the circuit is still on, we take the time t equal to 0 at some instant where the voltage is 0 and the current is positive maximum. Now what happens to the phasor diagram in this case? So you recall that we had said that our x-axis here is t equal to 0, that's the reference line that we have been having, and at time t we said the phasor is a vector directed at an angle omega t to the t equal to 0 axis, and this phasor is rotating counterclockwise with an angular velocity omega, and since the current leads the voltage by pi by 2, the corresponding current phasor would be given like this. So this angle is 90 degrees, and so the magnitudes of these are, this is Im is the magnitude of the current phasor, Vm is the magnitude of the voltage phasor, and if you take the projection along the y-axis, then this gives you the instantaneous voltage at time t, and likewise if you take the projection of the current phasor at time t along the y-axis, that gives you the instantaneous current at time t. So therefore let me make this point here, that is current leads the voltage by pi by 2, which is another way of saying that I becomes maximum t by 4 before the voltage does. So let us look at the charging and discharging of the circuit for a capacitive circuit. Let me redraw the current and the voltage with time for a capacitive circuit with the voltage shown in black and the current in red. Since my current leads the voltage by I by 2, that is by a quarter cycle. So when the voltage is maximum, the current becomes 0. So the type of curve that I have is something like this. Of course, it will again. Okay, so notice what's happening is this. Supposing this is my time axis and this is time t equal to 0, and this is the t by 4, t by 2, 3t by 4 and t. So look at what happens at t equal to 0. So this is my circuit. Let us suppose at that instant this side is positive and this side is negative. So my voltage is 0 but is increasing, and the current has become maximum, and current also is positive. So I have I greater than 0. So therefore there will be a charging current which will flow like this and will make this plate positive, and naturally this plate will become negative. Now, so this is what happens at between t equal to 0 to t equal to t by 4. So charging takes place. Now at t equal to t by 4, the capacitor plates are fully charged. The voltage has become maximum at that time, and for a brief time here it is neither increasing nor decreasing, so that there is no current flowing, as can be also seen by the current diagram. So let me label it. The red one is the current and the black represents the voltage. So what we said is that at t equal to 4 it is fully charged, and for a brief moment there is no current. At that instant. Now what happens next? So I am now going from t by 4 to t by 2. Notice from t by 4 to t by 2, the voltage is decreasing, though is positive. So therefore the current still flows, but notice now the current will flow in the opposite direction, making the right hand side plate less negative than it was, and of course since the positive plate is depleting its charge, it will also become less positive. At the instant t by 2, for a brief instant at this point, the plates have been fully discharged. So let me come back. So at t by 2, the plates are fully discharged. So in this cycle, discharging takes place. So left plate becomes less positive, and naturally the right plate becomes less negative. So the situation at that time is this, that I have two plates which have no charge, and this is my source there. Now let us now go from T by 2 to 3T by 4. Now notice what is happening in this part of the cycle. The current is negative and is increasing in magnitude. So what is happening now is this, that the direction of the current would be opposite. So the current would now flow in this direction, making this plate positive and that plate. So this side was minus, this side is plus. So the current reverses in direction, and plates are charged in the opposite direction. Once again, at 3T by 4, the voltage in the negative direction has become maximum, and once again, when you go from 3T by 4 to T, the discharging takes place. So this is charging circuit again. Discharging takes place now. Making the left plate less positive and the right plate less negative, till at time t we return back to uncharged plates. Let me take an example very similar to what we did some time back for the inductive circuit. In fact, we'll take essentially the same example, but with a slightly different set of numbers. So what is said here is this, that I have a voltage source which is giving me maximum 25 volts. So 25 sine omega t was my variation. This is V. Omega was 400 radians per second. And here I have connected it to a 10 microfarad capacitor. In the previous example, I had an inductor connected. So once again, my question is the following, that first of course we'll find out various quantities connected with this circuit, and then we say at the instant when V of t is minus 12.5 volts and is increasing in magnitude. What is the current? Well, first some numbers. My capacitive reactance, which is given by 1 over omega c, is given by 1 over omega is 400, c is 10 microfarad, meaning thereby 10 to the power minus 5 farads. So this works out to 0.25 into 10 to the power 3. So this is 250 ohms. The maximum current in that case would be Vm by Xc, which is 25 divided by 250, and that's equal to 0.1 ampere. Now my next question was, consider the instant when the voltage is minus 12.5 and is increasing in magnitude. In a similar situation, in the previous example connected with an inductor, I had seen that there are two solutions for omega t, but out of that, the solution for which the value is minus 12.5 volt and the magnitude is increasing is given by omega t is equal to 7 pi by 6. So I would point out from previous example. Then my I becomes Im sine omega t, but this time plus pi by 2. Im I have already found out to be 0.1 ampere, and this is sine of 7 pi by 6 plus pi by 2, which is 0.1 times sine of 10 pi by 6. The sine of 10 pi by 6 takes it to the fourth quadrant. So therefore, what happens is this, that I will get a negative value of the current, and that would then be equal to minus 0.1 into square root of 3 by 2, that's equal to minus 0.085 amperes. In this problem, I am also required to find out what is the time lag between the voltage and the current maximum. Now we have seen that the current leads the voltage by pi by 2, and so that is a time period of t by 4. So, and in my case what is given is omega equal to 400, but by definition of omega it is 2 pi by t. That tells me that t by 4, which is the time lag that we are talking about, is given by pi by 800, which is 3.9 milliseconds. Let me continue with another example. We can construct a voltage divider using a capacitive circuit. Remember that we could do that even with resistance. For example, if I had a, let's say, couple of resistances in series, then the voltage drop across the first resistor would be I times R1, and about the second resistor would be I times R2. So that enabled us to divide the voltage. Now this is the same thing that happens here, but let's see how it works. So this is a voltage divider using capacitors. Here also I use two capacitors in series. This, as usual, is Vm sin omega t. Let me take V of t to be equal to 25 sin omega t as before, and omega I will take it to be 400 radians per second. So the voltage division works like this. There is a capacitor here, which is, let's call it C1, equal to, let's say, 10 microfarad. There is another one in series with it, which is C2. Let's take it as 20 microfarad. So what happens here is this, that between this point and that point, there is a voltage V1, and between this point and that point, there is a voltage V2. Now remember that since the capacitors are in series, the charge Q at any instant in them is the same, but the voltage is different. Now in order to do that, what we need to find out is what is the reactance of the first capacitor. This is equal to 1 over omega C1. Omega is 400, C1 is 10 microfarad. So that we have just now worked out in another problem to give me 250 ohms. And XC2, since the capacitance is double, the reactance would half. So omega C2 equal to 125 ohms. Now these, of course, in a series they just add up, so that my net XC for the circuit is 250 plus 125 equal to 375 ohms. So therefore, my maximum current is Vm, which is 25, divided by Xc, which is just 25 by 375, which if you calculate works out to 67 milliamperes. This is amperes, this is 67 milliamperes. So Vc1 is equal to I times Xc1, so which is 0.067, I am writing it in amperes still, into 250, and that works out to 16.67 volts. Vc2 will be I times Xc2, and this is simply the same thing multiplied with 125, and that happens to be 8.33 volts. You can see that basically this voltage division has been in a 2:1 ratio. These are of course the maximum values of voltage across the capacitors, and the variation with time, which we have not shown here, is the same as that of the source, namely it varies as sin omega. Let's continue with some more examples that will help us in getting some of the terms that we have been using clearer. A 5 microfarad capacitor is connected to an AC generator with Vrms equal to 60 volts. We observe the peak current is the same as the maximum current to be 0.42 amperes. We are required to find the frequency of the source. So you remember that the relationship between V and I, and that is applicable to whether we are talking about RMS or the instantaneous values. So Vrms is IRMS multiplied by Xc. IRMS equal to 0.42 divided by square root of 2, because I have been given that the peak current is 0.42. So RMS value is obtained by dividing it by square root of 2, and that is approximately 0.3 amperes. And my XC then is Vrms by Irms, that's 60 divided by 0.3, which is 200 ohms. But Xc is also 1 over omega c, that's equal to 200. I have given C to be 5 microfarad. From this, it's trivial to see that omega works out to 1000 radian per second, which corresponds to a frequency f, because omega is 2 pi f. So f is 1000 divided by 2 pi, which is equal to 160 hertz. Before we conclude this topic, let me talk about power in a capacitive circuit. Remember that capacitors can store energy, and they don't dissipate energy but can return that energy that they have stored to other parts of the circuit depending upon what is the condition that's there. So my instantaneous power that's equal to IT into VT, and that's equal to IM VM. I had a sine omega t multiplied by sine of omega t plus pi by 2, which is the same as cos omega t. So that's equal to IM VM by 2 times sine 2 omega. So my average power is 0, because we had said in the first lecture that averages of things like sine omega t, sine 2 omega t, etc. is 0. So my average power is 0. The energy that is stored is given by half CV square. As you can see it here, that if you want to rewrite what is IT VT, you can write this as C times dV by dt, that's your dq by dt, which is same as I, times V. These are all the voltages across the capacitor plates. So this can be rewritten as d by dt of half CV square. And this is the amount of energy, which is of course positive. And that is, let's call it W. That W is given by half C Vm square sine square omega. Now let us look at the way the power changes. So let us look at what happens to the power curve in this case. In this graph, I have plotted the voltage V of t in black and the current in blue, and the power P of t, instantaneous power, is given by I of t into V of t. And since I varies as cosine and V varies as sine, what I get here is Im Vm by 2 into sine of 2 omega. So you notice that the period of the power is half the period of either the current or the voltage. And in the first quarter cycle, that is from here to t by 4, that is t equal to 0 to t equal to t by 4, You notice both current and voltages are positive, and so this implies that we are talking about omega t equal to 0 to pi by 2. So sine of 2 omega t remains positive. Now this is shown by the red curve here. So I is greater than 0, V is greater than 0, and naturally the power P, which is product of I and V, is also greater than 0. Here the energy is absorbed from the source. Power is positive means energy is absorbed. In the next quarter cycle, that is from t equal to t by 4 to t by 2, you notice that power becomes negative because though the voltage remains positive, the current has now become negative. So what it implies is the energy that was absorbed in the first quarter cycle is now returned to the source. And so here P is less than 0, the energy absorbed earlier is returned. And the same thing is repeated in the third and the fourth quarter cycle, namely in the third quarter cycle the energy is absorbed and in the fourth it is returned back again. Now if you look at this power curve, namely the way power is absorbed from the source and returned to the source, you will realize that in the quarter cycle in which charging is taking place, the power is always absorbed, and in the next quarter cycle when discharging is taking place, the power is returned to the source. So what we have done in this lecture is to talk about a circuit which consists of a source of an alternating voltage with a capacitive element put in there. We found out that in a purely capacitive circuit, the current leads the voltage by an amount of pi by 2, and we discussed how a purely capacitive circuit can be used for purposes such as being applied as a voltage divider and things like that.